In this tutorial we're looking at section 10.6, which is on water flow. So the rate at which the volume of fluid leaves a container is proportional to the square root of the height of the fluid in the tank, okay, or in the container. Okay, so it's just a bit of an idea. There's this Torricelli's theorem. They talk about it a little bit in the start of the book. Okay, but that's the gist of it. Okay, and to answer questions about water flow, we need to use the techniques of finding volumes and use related rates to set up and solve differential equations. Sometimes we need to use numerical methods to evaluate a definite integral. So we've got a couple of worked examples to have a look at. Okay, the first one is worked example 16. Okay, both the worked examples are quite long and wordy, so I haven't written them out, so a bit of space. Okay, but worked example 16, we've got a vase that's got a circular base and a top with a radii of 4 centimetres and 9 centimetres respectively, and a height of 16 centimetres. The origin O is at the centre of the base. The vase is formed when the curve y equals a times the square root of x plus b is rotated about the y-axis. So we have y equals a times the square root of x plus b. Okay, initially the vase is filled with water, but the water leaks out at a rate equal to 4 times square root of h centimetres cubed per minute. Okay, where h is the height of the water remaining in the vase after t minutes, set up the differential equation for h and t and determine how much time it takes for the vase to become empty. Okay, so what we've got is we'll draw a little picture. Okay, we've got a vase that looks something like this. Okay, it's 4 centimetres from the origin out to here. Okay, and it's 9 centimetres out here. And we know we're 16 centimetres high. Okay, we know that we've got some volume of water in it still. Okay, whose depth is h. Okay, so that's what we've got. Okay, so we know the curve, this curve here, passes through the point 4, 0 and also through the point 9, 16. Okay, so we sub 4 and 0 into our equation. So we're going to get 0 equals 2a plus b. Okay, and we're also going to get 16 equals 3a plus b. Okay, when we solve that simultaneously, okay, we get a value for a, which is equal to 16, and b that is equal to negative 32. So that means our equation becomes y equals 16 root x minus 32. Okay, so the vase is formed when our equation between x equals 4 and 9 is rotated about the y-axis. So remember, that means our volume equals pi times our integral from 0 to h of x squared dy. Okay, so that means that we need to rearrange our equation, okay, for x squared. Okay, when we do that, okay, well, we're going to take away our 32, divide by our 16 and square it. Okay, which means we end up getting x squared, okay, equals, so, and we wouldn't just square it. Squaring it would just take us to x. We need to x squared, so we would actually have to quadruple it. So we're going to get x squared equals y plus 32 to the power of 4 over 65536. Okay, so that means that our volume is equal to pi times the integral from 0 to h of our y plus 32 to the power of 4 all over our 65536 times dy. Okay, so we're getting there. Okay, so that means, okay, that we get an equation dv dh, okay, which is going to be equal to well, and this is using some of our numerical techniques that we used earlier. Okay, that we find dv dh equals pi times h plus 32 to the power of 4 over our 65536. Okay, and if we set up our chain rule, okay, we're looking at dh dt is equal to dh dv times dv dt. Now, dh dv is this flipped over. Okay, so we're going to get then it's 65536 on our pi times our h plus 32 power 4. Now our dv dt, we actually know that's our 4h, but we're actually reducing our volume. Okay, so it's going to be negative 4 times root h. Okay, that means then our TDH is going to be equal to, well, we can say it's negative pi times our h plus 32 on 4 over 262,144 root h. Okay, just doing a bit of arithmetic there. So then, because that means then that t is going to be the integral of this, okay, of negative pi times h plus 32 to the power of 4 over our 262,144 root h dh. Okay, now we're actually going to go from 16 to 0. Okay, we could have gone from 0 to 16. Okay, but what that would have meant is that we would end up with a negative answer. Okay, and that's because we would be talking about filling it, not emptying it. Because we're emptying it, we won't go from 16 to 0, so we end up with a positive answer. Okay, so that means that when we work this out, we get t equals 205.59 minutes. Okay, so if we just look back at the full process that we've done here, okay, we want how much time it takes to become empty. Okay, so we needed a t. Okay, because we had our two things, we're going to have to set up a chain rule question. So we needed to end up with something in terms of t. Now we couldn't use dv dt because we're given that. Okay, so we wouldn't have needed. Oh, and sorry, we could set up an equation for dh dv. So we wouldn't need dh dt, so we could find out our t. Okay, so we've gone through, we've worked out what our equation is. Okay, we found out what our volume was. Integrate that with respect to the height. Okay, and then we've also had our dv dt, set up our chain rule to get our dh dt, invert it to get our dt dh, and then we've integrated that to get back to our t. Okay, so a little bit to it. Okay. Now we're at example 17. Okay, another vase is formed when part of the curve x squared on 16 minus y squared on 500 equals 1. Okay, for x is greater than or equal to 4, it's less than or equal to 6. Okay, so that's our equation. Okay, and y is greater than or equal to 0. Okay, is rotated about the y-axis to form a volume of revolution. The x and y coordinates are measured in centimetres. The vase has a small crack in the base and the water leaks out at a rate proportional to the square root of the remaining height of the water. Initially the vase was full, and after 10 minutes the height of the water in the vase is 16 centimetres. Find how much longer it will be before the vase is empty. Okay, so remember the vase is formed when the curve is rotated about the y-axis. So remember we've got v equals pi times our integral from a to b of x squared dy. Okay, so we need to get x squared by itself. Okay, so we need to determine the height above the vase. So find the value of y when x equals 6. Okay, so when x equals 6, okay, if we put 6 into our equation, we find that y equals 25. Now we would have had to take the square root of it at some stage to get our 25, but we ignore the negative one because we know y has to be larger than 0. Okay, so what we find out is that we've got a vase that looks something like this. Okay, and this is our minus 4, our positive 4, our 6, our minus 6. Okay, this is at 25. Okay, and we know from here to here is out to 6. Same on the other side. Okay, and we've got some volume of water in our vase. Okay, it's got some sort of height. Okay, so what we need to do is rearrange our equation to make x squared the subject. Okay, so when we do that, we find that x squared is equal to 4 outside of 500 plus y squared all over 125. Now I've just skipped the steps there just to save on the arithmetic and a bit of room. Okay, so that means that when we sub this into our equation, what we do is bring our 4 on 125 out. Okay, so we can say our volume equals 4 pi on 125 outside the integral from 0 to h of 500 plus y squared dy. Okay, so that means that our dv dh is going to equal our 4 pi outside of 500 plus h squared all over our 125. Okay, once we integrate this and sub in our terminals. Okay. Since the water leaks out at a rate proportional to the square root of the remaining height of the water, what we can say then is that dv dt is equal to some value k times the square root of h. Okay, and k is some positive value. Okay, well we know our dh dt is equal to our dh dv times dv dt. Okay, so our dh dt then, dh dt, well we're going to invert this one here, okay, and times it by our negative k times root h. So our dh dt can be written as negative 125 times k times the square root of h all over 4 pi outside of h squared plus 500. Okay, so when we want to find our, we need to flip this and make it dt dh. Okay, and then we're going to end up with 4 pi times h squared plus 500 on the 125 k times the square root of h. Okay, and what we do is we say let a equal our 4 pi on 125, because that's just a constant, so just to make our work a little bit easier, so we can say our dt dh is equal to then negative a outside of h to the 3 on 2 plus 500 h to the negative a half, just by simplifying our powers here. Okay, so our squared and our square root becomes our 3 on 2, okay, and our square root just becomes our negative a half. Okay, that means then that our t is equal to minus a, because that's just a constant, outside our integral of our h to the 3 on 2 plus 500 h to the negative a half dh. Okay, and we can integrate that, so we get our t equals negative a outside of our 2 on 5 h to the 5 on 2, okay, plus 1000 h to the positive a half plus c. Okay, and c is our constant of integration. Okay, so what we need to do is we need to use some of our initial conditions. So we know when t equals 0, h was equal to 25, because that was our maximum volume. Okay, so when we do that, we find that a is equal to c on our 6250. Okay, since after 10 minutes the height of the water in the vase is 16 centimeters, okay, then we also we can also set our h and t equal to that. Okay, And what we do when we run through all that, okay, we find that the C value that we've got, okay, is equal to 33.96. Okay, that's by subbing in T equals 10, H equals 16, okay, into our equation down here. Okay, then we can also find that our C is our 33.96. Okay, so what that means, okay, is this basically means that our, down here, sorry, okay, we need to think about our height here. Well, when our height is equal to 0, okay, that means our vase is empty. Okay, so if H is 0, then all of this in here is 0, times by our A is 0. So when the vase is empty, okay, okay, T will equal C, so will equal C, so T will equal 33.96 minutes, okay, to empty the vase. However, we already know that 10 minutes have passed, so it will take an extra 23.96 minutes to empty, okay, from being full. Okay, so basically what we did is we set up our equation and drew our picture. Okay, we rearranged for x squared so we could find our volume. Okay, we integrated our volume so we could our dVdh. Okay, we knew where our dVdt was, but we kind of had to set it up a little bit by saying another constant, so that was a little bit of a trickier step there. Okay, set up our train rule here. Okay, and so we could work out our dHt. We need to flip that. Okay, so we could integrate it to get our t value. Okay, and then we had to sub in some values we knew so we could get our c value. Okay, which was in fact the time it takes to empty. Okay, so these questions are probably a little bit trickier than some of the ones that we've had in the past. Okay, so here you go, we're getting through them. There's not quite as many as in previous sections, but they probably will take you a little bit of time to get through them.